Okay. Good morning, everyone, and thank you so much for joining our training. And I'm Yang Liu from Brooker, and I will take care of the training today. And I'm so happy to come back again in this room. Last year, we gave a brief introduction, the quarter brief about the atomic force microscopy. So this week, we will introduce some applications, especially in the electric applications of the atomic force microscopy to show what we can do with these tools. So at the beginning, I still would like to show this page, this slide, about how you can reach us if you need any support. Anytime you find something wrong with this AFM machines or you need some support about your applications, you can reach us either using the phone, emails, or even in WeChat. Any ways you can reach us. Okay. Okay. Let's go directly to our topic today. So, our topic today is about the so-called electric field force microscopy, the one classic application of the AFM. That's the so-called EFM. So before that, I would like to give a brief introduction, not introduction, I think a brief review about the AFM for you guys again. So the AFM. So the purpose we would invent this instrument, I think it's invented in the 1980s. And at that time, we just want to invent one instrument to achieve three goals. First, we want to get the morphologies at three-dimensional. So we want the X, Y, and Z. Second, we want our machines to reach the real nanometer scale. So the resolution is at a nanometer. And the third, if we can get it done in vivo or in situ. That's the three goals we want to achieve using the atomic microscope, this instrument. So finally, we invent this kind of machines. If we have a probe, and then we let the probe to scan on the surface. And then at this time, we want to get the morphology of our sample. So how to achieve that? We would like to do that in this way. If we let our probe to trace on the surface, and then we can achieve the probe trajectory equals to the morphology. And then we will just record the probe trajectory in the software. And that gives us the morphology of the sample. Quite easy, right? So, so the key here is how can we let the probe always trace the surface? So many ways to achieve that. So we choose in this setup. If you want the probe to trace the surface, that means if we want the probe to always touch the surface of your sample, in the physical ways, it equals to the trace equals to the distance between the tip and the sample. It should always equal to a constant. That means we keep the tip touch the surface. That's the physical meaning of the tip, the trace. How we achieve that? If we can find a function, this function is related to the tip sample distance. If we can keep this function as a constant, then we achieve the distance between the tip and sample is constant, and then the tip is traced on the sample. And then we let the tip scan back and forth, back and back and forth. We record the probe, how it moves, and then we get the morphology. That's the brief idea of the atomic force microscopy. So the K here is what function we can use to get this step down. So the function we found here is the force. So we all know our tips. The tip is just one material, and the sample is another materials. But if you look at in the atoms way, it's just a bunch of atoms. And our samples is also a bunch of atoms. And the atoms, we all know it consists of one nucleus with positive charge and several electrons with negative charge. Okay, so once these two atoms get closer, there will be a repulsion between the two nucleus, and the electrons, it also has the repulsions. So we would know there will be, oh, let me put it here. So it's quite important. So we can get an interaction force, and this will be a distance between two atoms. Once they get closer, it will sense. Let me use the red pen. It will sense an attraction between the nucleus and the electrons. And once it gets closer, it will definitely add a repulsion. That's the interaction force between two atoms, right? And then we expand this concept to, if we have a probe and a sample, it will be similar like that. And you guys know it very well if we get these curves together. Something like that, right? That's the Lennard-Jones interaction, right? That's just the basic of our quantum mechanics. And so no matter how, we would know the interaction force between the tip and the samples is definitely a function of the distance. So if we can measure the force and make sure the force is a constant, and then we will keep the distance between the tip and the sample is a constant, and then we let the tip move forward and move back and forth. We get the morphology done, right? Okay, that's the concept of our AFM. So what we do next is we need to measure the force. How we can measure the force? We make this tip. We attach the tip to a what? To a cantilever. To a cantilever. If the tip sense a force from the sample, it will bend this cantilever. And what's next? We shine the cantilever with a laser, and the laser, the cantilever will reflect the laser to a detector, right? And then on the detector, we can get the position of our laser beam, and we measure the position of the laser beam. We know how the cantilever is bent, and then we know how the cantilever is bent, we know this force, right? So we can get this function like that. So we would like to get the distance, tip sample distance as a constant. We transferred it into the force as a constant. And then the force, we measure it as the deflection of the cantilever. We make sure that is a constant. And finally, the deflection, we measure it as the laser signal. And we keep that as a constant. And then our tip is moving forward and backward. We get the trajectory here. That's done. That's our AFM, right? That's how we do this experience. So every time you go to the AFM, every time you go to the AFM, you mount a probe and you align the laser on the cantilever, and then you measure and then you adjust the detector and the down, and then you get the laser detector signals. And once you are on the software will ask you to keep this detector signals, which is vertical as a constant. And then that's what we did here. Okay, that's the total idea of our atomic force microscope. Okay, so the idea here is, let's go back to the Dennard-Jones interactions. For this function, for this interaction, we would know it will only take place if these two atoms get closer to each other. So we would call this interaction between two atoms, they are short range. So it will only happen when the tip is get closer to the sample. And if the tip is away from the sample, this interaction is gone. So in our topic, we would call this Lennard-Jones interaction force. We just gave it a nickname. We call it atomic force, okay? In principle, you will know this so-called atomic force is just the electric field force, right? It's just between the force between the positive charge and the negative charge, or positive charge and the positive charge. So the atomic force in principle is the electric force. But we will consider it's a kind of short range electric force. Okay, so that's the atomic force microscope, and with that we can get the morphology of the sample, and then use this theory, we can get the morphology. Yeah, we can get the morphology, and the morphology is just how the samples looks like. But in today's material study, that's not all the whole story, because we would like to know what's the materials on our sample. If, for example, if we have a binary surface, we have a material A and we have material B. For example, the tire. We have tire, right? Tire, there is a rubber and the carbon. If we are studying a binary samples, we always want to know more details about this material rather than its morphology. So, for example, we want to know how these two materials they bind with each other, and then we need to know the distributions of these two materials. But as we talked, the AFM from this theory, from this setup, we only know the morphology, and we cannot tell which one is which. we don't know the materials. Briefly, the AFM is blind. They just know the force, or they just know the atoms. They don't know what materials. So we need to find a way to distinguish different materials using the AFM setups. So how? AFM tip is blind, so we need to give it our eyes to do that. So if we know the properties of these two materials, they are different, then we can find a way to distinguish that. For example, in tires, we have rubber, we have carbon. So if we are studying this kind of the tires, and for example, we get its morphology, something like that. And then how can we tell which part is rubber, which part is carbon? We take a look at this sample and we think about it. Okay, what's the difference between the carbon and the rubber? So the first thing came to my mind is they are different in the mechanical properties. I would say rubber is soft, carbon is kind of hard. So if we can tell which part is soft, which part is hard, then I can distinguish them. So how I can do that? So there is a so-called quite classic applications in the AFM that we can measure the stiffness or the modulus of the sample. We use a tip. So how can I distinguish this brush and the brows? The brows is hard, the brush is soft. So if I squeeze on it, the brush can be squeezed easily. But this mouse is hard. If I squeeze, nothing will happen. So if I use the tip to squeeze, of course not squeeze, it's just a compress on this surface. If the surface is soft, and then I know that part is the rubber. If that surface is hard, then I know it's kind of carbon, right? So I can use the probe to compress on the surface. The idea here is I use the mechanical property. I would like to use the modulus to distinguish the rubber and the carbon. That's right. That's my idea. Okay. And then the scientists from the tire companies, they give us more headaches. Okay, they gave me a sample, and he told me, you use the mechanical properties to distinguish the rubber and the carbon. It works, but it not works every time because we know the carbon is not always on the surface. Sometimes we get a surface. There are some carbons buried inside this rubber. If you use the probe to compress on it, you always touch the rubber. You cannot touch the carbon. Then what can we do? Okay, so the next when we go back, that's the real story. When we go back to the about 2000 years, it's about 2000 years. Our customers from the tire company give the AFM companies this kind of idea. Okay, how we can distinguish that? So we cannot use the mechanical properties to distinguish rubber and the carbon. And then what next? Then we still need to find a way to tell the difference between two materials. We don't only have the mechanical properties, we have more properties difference. For example, when we take at these two materials, of course, this one is hard, this one is soft, but they have more differences. This rubber, we would know is isolated, right? It's not conductive, but the carbon is a conductor. It's conductive, right? So if we can measure the conductivity of these materials, it can be easily done, right? And at that time, we have a quite classic application. That's the so-called conductive AFM. This will be our topic on Friday. Okay, at that time, we have the so-called conductive AFM. The conductive AFM is just used to measure the conductivity of the sample. If we can get the conductivity mapping of our rubber surface, the conductive part will definitely be carbon, and the isolated part will, of course, be the rubber. Okay, so how we can do that? The conductive AFM has a basic idea is we have a sample, and we let the probe to touch on the sample. We apply a voltage on the sample, and we grab an ampere to measure the current inside this loop. Quite simple, but we have an idea. If the carbon is buried inside the rubber, that means every carbon is just wrapped by the rubber. The rubber is isolated. And then we would imagine in the loop, there will be some carbon, but the carbon is buried inside the rubber. It cannot form a conductive loop. So it will definitely no current at all. So this idea still does not work. Okay, but it gives us an idea. Okay, what's next? What's next? And then we take a look at this rubber and the carbon. Yes, this one is isolated. This one is conductive. And the conductor and isolator, they are not just the difference in the conductivity. It has also another difference at the dielectric, right? So what's the dielectric? If we have a conductor here, if we have a conductor, say we call this conductor what? Aluminum. And then if I place a positive charge here, and this positive charge will definitely cause an electric field, right? What will happen? There are many free electrons inside the aluminum, and then the electrons will be connected here, right? And then it will left all the positive charges here, right? And it will cause the electron field inside the aluminum to be zero, right? That's the so-called classic electrocharge shield, right? Everybody knows in our high school. That's the conductor. Okay. What will happen if we place isolate here? Same story. We have an isolate here, say rubber. And we again place a positive charge here, and it will apply an electric field. What's next? So this kind of polar, this kind of rubber, it's just there's no free charges. There's no free electrons inside these materials. So, but again, it still has some electrons. So it will be polarized a little bit by these electron charges, by this electric field. So it will be slightly negative charges on this side, and there will be slightly positive charges on this side. We call this kind of we call this kind of phenomena the polarization. Right? That's the idea. That will be happen in the isolator. So for the conductor, it will be completely polarized. All the negative electrons, all the negative charges will be facing into the source of the electric field, and it will cause the inside of the materials, there will be zero electric field. So then it will be a strong interaction between this force, this phase, and the source. And then for the isolator, the interaction here is almost zero, right? That's the difference between the conductor and the isolator, because they are quite different in the dielectric properties. So we have an idea about the tile stories. If we can use the properties in the dielectrics properties, if we get a positive source, positive charge on the surface, the carbon, there will be a strong interaction between the positive charge on the carbon. If this positive charge is on the rubber, there will be a quite weak interaction. And then we can definitely use this way to distinguish the rubber and the carbon. That's the idea of the so-called electric field microscope. Okay, so let's go to this topic. So for the EFM or for the or for this kind of thing, we have an idea. If we want to measure some force rather than the atomic force, what we can do? We only know the AFM probes is good at sensing the force between the tip and the sample. So the AFM probe is a way to measure force. It can measure the atomic force. It can measure the interaction force between different charges. So how can we distinguish them? We find a typical or we find a property of the atomic force is that the atomic force is short range. If we want to measure another force, we will use this kind of properties. So the AFM, the atomic force, will only take place at short range. That means it will only happen if the tip is touch the surface. If we grasp the tip away from the surface, the atomic force is gone. So if at that time, if they still sense some force, it will definitely be another source. For example, the electric field. So we have an idea to call this interleave scan. The idea of the interleave scan is we scan the surface twice. The first time we let the probe to trace on the surface. Once it traces on the surface, it can sense the atomic force between the tip and the sample. And then at the second time, we lift the tip up. And at that time, when we tip is away from the surface, the AFM is short range. Once the tip is away from the surface, the AFM is gone. We cannot measure the AFM, the atomic force anymore. And then we let the tip to scan on the surface, on top of the surface. If at that time we can still sense some force, this force will definitely be some non-range interaction force. This non-range interaction force can be many things. magnetic field, electric field. Okay, so the idea is just like that. So we scan the system, we scan the surface twice. The first, we use the atomic force to get the morphology. Second, we lift it and to scan the surface, we will get some long-range interactions, for example, here. So the typical applications of this interleave scan is the magnetic field and the electric field. For example, this slide here shows you the EFM. For example, we have a surface. On the surface, this black line is the morphology of the surface. So our tip, when the tip is touched on the surface, it gets the morphology. And then we lift the probe, the morphology is gone, right? It cannot sense the atomic force anymore, but there are some charges on the surface. The charge on the surface will be the source of electric fields. It will generate electric field, and if the tip can sense the electric field interaction, it can sense some force. And then this force will be from the charges, right? So in this way, we can tell which one is charged, which one is charged, which part is not charged. That's the idea of the interleave scan. Okay. The interleave scan, in the real way, it happens like that. So our AFM, we want to get the morphology. We let the probe always trace on the surface, so it controls the difference, the distance between the tip and the surface. And then how we can achieve this kind of so-called scan? So the probe should move every point on the surface. So in a typical way, in our AFM setup is the so-called raster scan. The raster scan is scan back and forth, back and forth, back and forth. And then we get the surface. This kind of scan is the same as the screen, television, everything is using this kind of raster scan. So every raster scan, it has two lines. It will be a trace moving from left to right, and there will be a retrace. We get the back, forth, back, forth. So all the trace lines, they are parallel with each other. All the retrace lines, they are parallel. So the AFM will be two frames. One, they formed by all the trace lines. And in our AFM software, you will see a direction trace. And then for all the retrace lines, we form a frame, and in the software, you will say it's retrace. So every time you will get two frames, anyone you like. Basically, in our AFM, these two frames, there will be a slightly difference between the because the trace and the retrace, they are not completely same, but it's almost the same. It's so in our software, you can choose any one of them. It's okay. Okay. If we want to do the interleave scan, the interleave scan, as we show here, we scan it twice. So in our in current AFM setup, we insert another scan between two trace retrace. So the scan will be something like that. We insert a second, we insert another scan layers. So we will call it interleaved scan. The interleaved scan and the morphology one, we call it main scan. So in the software, you will see two sets. One set is all these black lines. The black lines, the probe is traced on the surface. And the second set is this dashed lines. In the software, we call it interleave scan. So the interleave scan, it also has the trace and the retrace, right? But in our systems, we will show it here. So we do a scan, and let me show it here. So we do a scan, trace, retrace, and the interleave trace, interleave retrace, trace, retrace, interleave trace, interleave retrace. Okay, and then we separate them. So at this time, we should have how many frames? We should have 4. One is trace, one is retrace, one is the interleave trace, one is interleave retrace, correct? Okay, so as we said, there will be a lift motion. The probe should lift from the surface to get the long-range interaction force. So it will happen in web. In our setup, we make this lift motion at the trace. So every time you do this kind of interleave scan, you will see the lift motion at every beginning of the trace. Because at this line, we're on the surface, trace, retrace, and then we want to lift the probe. Lift the probe, it took some time. It's just milliseconds, but it takes some time. So you will see a lift motion here. So this lift motion will take place on the beginning of the interleave trace. And then interleave trace, interleave retrace, and then it will what? The probe should go back on the surface, it will drop down. And this drop down will happen on what? On the beginning of the main trace. So in our setup, the lift is on the beginning of the interleave trace, and the drop is on the beginning of the main trace. Okay, that's the difference. So if we don't want to say this kind of lift drop, what's our best choice? We take a look at the main retrace and the interleave retrace. So that's why our software default setting, they shows you only the retrace frames. Okay, that's the setup. So in the afternoon, when you take a look at the so-called interleave scan, you will say we always capture the retrace directions. Okay, of course you can check the trace motion to say how this lift and the drop down take place. Okay, that's the idea. Then in our AFMs, there are several interleave modes. The interleave modes we would like to use are this kind of lift. In the software, you will see 2 lift modes. One is lift by sensor. We still give a brief review about the sensor here. That's just some idea about the piezo response tomorrow. So we will give it here. So what's our scanner? We said the probe trace on the surface, and then we use something to drag the tip to scan on the surface. This we call it a scanner. And the scanner is in our AFM setup. We made this kind of scanner with the piezo electric ceramic, the so-called piezo tubes, that's something like that. So this kind of piezoelectric ceramic, you guys know it very well. That's the piezoelectric, the response. We will go through that tomorrow. Is if we apply a voltage on this tube, this voltage will cause a deformation. And then we apply a voltage on this tube, the tube will move. And then if we bind a tip on this tube, we apply voltage, the tube moves, then the tip is moved back and forth, back and forth. That's the piezoelectric force. I'm sorry, that's the piezoelectric effect. And we will go through that tomorrow. So that's our scanner. So how we control the probe is moving on the surface. We just apply voltage and then we let the probe to move on the surface. But it has the idea that how I know the position of my scanner. So in our setup, we place a position sensor. We place a position sensor, we attach this sensor to our scanner. So we apply voltage, and then this tube is moved due to the piezoelectric effect, and then the probe is moving back and forth. And then from the position sensor attached on the scanner, we know the exact position of my tip. So that's the purpose of this position sensor. And this position sensor, we have three of them, X, Y, and Z. And the Z position sensor is quite famous to you guys. That's the height sensor channel. That's the height sensor channel. That's the every AFM images you kept when you're playing around the icon in MCPI, right? That's the morphology. So every channel we have this XYZ position, XYZ position sensors. So let's go to our lift. The probe at the beginning is on the surface, and then we want to lift the probe, say by 100 nanometers. And how we achieve that? We have the scanner. We calculate if we want the scanner to shrink 100 nanometers, how many voltages we should apply. And then we apply this voltage on the scanner, the probe lift up. But what's the exactly lift up distance? We don't know. So we can tell the lift up distance from this Z sensor. And then from this Z sensor, we can know the exact lift up position. And then we use this back to adjust the voltage to make sure we lift up by 100 nanometers. So this kind of setup, we call it a closed loop. So we can say the difference. There's a lift. There's a lift by sensor. So the lift is from the software, we always use the 100 nanometer as an example, okay? So from the software, you apply a 100 nanometer lift distance. And then from this 100 nanometer, the software will calculate lift voltage, and it applies on the scanner. And it applies on the scanner. The scanner shrinks, the tip is away from the surface. If this calculation is correct, this distance should be 100 nanometers, right? But we know everything about this, the piezo effect. The piezo effect is non-linear. So that means this 100 nanometers calculated into the lift voltage, it does not guarantee we lift 100 nanometers. We don't know. Okay, then what about this lift by sensor? Again, we have the 100 nanometer from the software, and it will generate a lift voltage. It applies onto the scanner, onto the tip, and then the tip is away from the surface. And then there is a position, there is a Z sensor here. And this Z sensor can directly read the lift distance. If this lift distance is larger than 100 nanometer, what it will do? It will tell this distance into this lift voltage. It's too large. Reduce the voltage, and then it will reduce the voltage. If this lift distance equal to 100 nanometers, the Z sensor will tell the lift voltage. You are correct. Stop. If it's smaller than 100 nanometers, it will tell the lift voltage, make it more, until we go to the 100 nanometers. So this kind of setup, it guarantees the lift distance is 100 nanometer, and we call this kind of thing closed loop. It's at the Z direction, so it's Z closed loop. Okay, that's the difference between the lift and the lift by sensor. Lift by sensor will guarantee your lift distance. So we recommend you to use the lift by sensor. Okay, but in the we have some users of the multi-mode. The multi-mode does not have this sensor setup. So the multi-mode just use the lift. That's enough. Okay. Hope I explained it. Okay. The difference between the lift and the lift by sensor. Okay. We have some researchers, users. They are from the they are studying this kind of electric loops. You will know this setup. It's more complex, so you can tell the response time. The response time on this setup, it should be slower than this, but it's just a slightly slower. So if you want your response, if your purpose is the accuracy distance, choose lift by sensor. If your purpose is response time, you can choose this one. Okay, that's the difference. Okay. Finally, let's go to our lift mode. So we remove this Nana Jones. We keep this force. So this line, we call it AF, atomic force. And we know it's short range. And then we can go back to our electric field or the magnetic field. Both interaction force. For example, for electric field force, the famous rules to define the electric field is the Coulomb rules, right? Coulomb laws. The force is equals to a constant, and is distance square and quantity one, quantity one, quantity two, that's the column rules. Okay, so the electric field force is proportional to the distance negative square. So, but this one we can tell this kind of force is a long range force. So this force will be, if we place it in this interaction force distance loop, it will be something like it's long range. Sorry, I changed it more dramatic. So the AFM, the AF, okay, it will be something like that. It's quite short range, but the electric field is long range. That's the repulsion between same charges. If we have different charges, it's attraction, right? So that's the attraction. So the electric field force is just it's a long range force, but no matter how, it depends on the distance. So our idea here is we want to tell which part is charged, which part is not charged. But the force itself depends on the distance. So if we want to measure the force, we want to make sure this force is it has a fixed distance, right? So in our lift setup, we scan twice. The first is on the surface, and once it scans on the surface, the system will remember the trajectory of this main scanning. And then on the second scan, on the lift scan, the probe lifts the surface by a defined distance. And then the probe should scan, follow the same trajectory of our first scan. As such, the distance between the tip on the surface is a constant, is equals to the same lift height, right? So in our lift scan, we will do it in this way. First, get the morphology, get the main scan. On the second, on the lift scan, it follow the same trajectory, and as such, we control the distance as the same. So we get the interaction force. At each point, it has the same distance. Okay, that's the idea of our lift scan. So that's why in the software you will say you will say a third interleave modes. That's the so-called linear. In the linear, in the lift scan, the probe is moving at a constant height. In principle, these modes can tell us what's the difference between at each point, but in the physical ways, we don't like this one because the distance between the tip and the sample is always changing. So we provide this option, but in the science, it's not that useful. So choose lift or lift by sensor. Okay. So that's the so-called the EFM. So we don't talk about that. So we play around with the mathematics here. Okay. We get the idea of the so-called the EFM. We are using the lift mode. We use the lift mode to detect the electric force. We detect this long-range force. That's the idea. So how we really measure this kind of long-range force? So we keep the mass, we keep it here. That's the, sorry, that's the AF. That's the EF. Okay. Oh. Then let's go to the detection. So the idea here is we use the lift to measure the so-called the long-range electric field force. So how we use the AFM setup to measure this electric field force? So let's jump this way. We go back to the we will go back to the mathematical a little bit. So we have a probe. And the probe will have interaction with the force, with the sample. Okay, so that's our AFM setups. And then we make this, we establish a model first. So this kind of probe, there's a sample, there will be an interaction force. And we give the name of this force. We call it the force between tip and the sample. Okay, and this force is detected by the cantilever, and then the cantilever has detected by the laser. That's the whole idea of the AFM. Okay, then we make this model to be something like that. We consider our probe as a point. It has a sample. It has an interaction force on these points. Of course, this point is not just a point, it's the probe. So it should have a mass. Okay, so we study on this, we study the force on this probe. So of course it has the gravity, right? But the gravity is so weak, so we ignore the gravity. We ignore the gravity. So we take a look at this probe, because this probe is attached to an cantilever. The cantilever can bend, and the bend of the cantilever will cause a what? The cantilever will play around like a spring. It will apply an elastic force on this probe. And what this spring's force looks like, it will follow Hooke's law. That means if the deflection is large, then this force will be large, right? It will follow the Hooke's law. So we place a coordinate here. If we place this mass, if we place the point in this scale, and this scale is at z direction, and we define the zero, we define the zero position, means the deflection is zero. Okay, we define the deflection is zero. So at these points, we can definitely know the probe will have the first force. The first force is from the spring, from the deflection of our cantilever. And the deflection of this cantilever, it follows the Hooke's law, so we will define it as the equals to the negative k times z. The k, we call it spring constant. That's the number on the back side of your probe box, right? So that's the first force. That's the first force we have. Okay, so let's consider it in a quite simple way. If our probe in vacuum and the low interaction force between tip and the sample, and then this force, and then this equation will be only this one, right? the force equals to the to the deflection of the cantilever. So according to the Newton's law, what will be this one? It will equals to the mass of the probes times the second derivative of z, acceleration of the z, right? So, and this one we will get a function, we will get a formula like that, the m times equals to the negative kz. Okay, the solution of this equation is quite easy, right? The z will equals to a cosine omega 0 t. What's this omega? We don't know. We take it back into this equation. We will get the left side is m times a negative omega square cosine omega t. Right side is negative k a cosine omega t, right? So we can tell the omega square equals to the k divided by m. The omega equals to the square root of k o m. So what's this omega? We call it resonant frequency. And in our AFM, we usually call it omega 0. What's the omega 0? It's just on the back side of your probe. For example, scan assist air probe, the frequency of the scan assist air probe is 75, right? That's the basic of our AFM. So a little bit review about the AFM principle, right? So we have the omega 0, we have the k, so I write it down here. So for each probe, now it has k, it has omega 0, k o m. Okay, quite easy. Second, we make our system more complex. We are not do the experiment in vacuum. No, it's not in vacuum. So we usually get it done in air, in solution. Everything is not in vacuum. So we are in a fluid. This fluid could be solution, could be air, right? Again, we don't have the interaction force between the tip and the sample. Our probe is free again. So this force, the Newton's law is always used. Second, we have the deflection of the cantilever. What's next? We would have a hydrodynamic force, right? We would have a hydrodynamic force caused by the fluid. So this kind of hydrodynamic force, usually we will define it in this way. In this hydrodynamic force, the hydrodynamic force, we would sense it in our daily life. If you run in the wind, if you run faster, you will sense the wind will give you more frictions. So this hydrodynamic force is all, of course, negative, and it's proportional to our speed. So it's proportional to dz over dt. And the coefficient, we will call it viscosity, right? We will call it viscosity. So that's our function. That's our equation here. So, and this equation, we don't spend time to solve this solution. We just give it out, okay? We just give it out. So the finally, again, it will be Z will equals to A, and it will be let me say, it will be still something like sinoid or cosine of the functions. And the results, I just write it down here. It should be equals to the think omega 0 omega 0 square and minus omega should be omega 0 divided by q square and t, and then it will be here should be e minus we think should be e minus omega 0 t divided by q, something like that. Okay, that's the results. This kind of function, how it looks like is it's a cosine function, right? So it should be something like this. But its amplitude is also related to time. So the amplitude will reduce against the time. So the function will be right? Will be something like that. So we call it damped oscillation. Something like that, okay? That's another function. So at this time, we will have another property that's the so-called Q. And in the Q, we don't solve the functions completely, but the Q is defined. Should be eta yeah, something like no. Should be something like that. Yeah, it's something like that. It's just proportional to the m, and it's also depends on the eta. So if your eta is small, the q will be large, and the q we call it factor. Okay. Finally, we get something related to our our probes, and then what's next? So we are in fluid. We don't want any interaction force. But at this time, we want to vibrate our probe. Why we want to do this step? We have in AFM, we have a quite famous scanning mode. That's the so-called tapping mode. So in the tapping mode, we want our tip to tap on the surface and then to let the probe follow the trajectory of the surface. And in this tapping mode, we would get the morphology of the surface. But in the tapping mode, in this tapping mode, we would get no touch. I'm sorry, no friction of the surface. because the probe is not always touching the surface, it's tapped on the surface. So in this tapping mode, we would drive the probe to oscillate on the surface. So how we achieve that? We would apply a drive force. So so we apply a driving force. This kind of driving force, we show it in the slide here. We show in the slide here. So the probe has a deflection. The probe has the spring force from the cantilever. It has the messed up again. There should be no two. It has the hydrodynamic force. It has the hydrodynamic force. And then we want it to do this tapping mode. We apply drive force. That's all the three force on these probes. Again, there is no tip sample interactions. And then this kind of solutions, this kind of equations, we solve it. We will get two solutions. One is a steady solution, and another one is transient solution. And if you take a look at this transient solution, it's just this one, right? It's just this one. And the steady solutions is we drive the probe to oscillate at a defined frequency. This defined frequency, we call it drive frequency. So, and then that's the final solutions of the movement of the probes. So from that, we can draw it something like that. So the probes now in this way, now the probes has two solutions. One is transient. We don't look at it because the amplitude will reduce against the time. So this one will reduce in a short time. It will only has this one stays. So we have a transient plus a steady solution. The steady solution is A cosine omega t and reduce a phase. So this omega is from the driving force. So we would tell the probe should be oscillate at omega, and the omega we call it the drive frequency. Okay, so the probe will just oscillate at this fixed frequency. And then what's next? We get the solutions is like that. The A is equals to something like that. A little bit complex. Okay, then we can go back to this slide. If our omega equals to the omega 0, what will happen? If the omega equals to the omega 0, it means the drive force, its frequency is at resonant frequency, omega 0. Of course, it will happen the so-called the resonance. Okay, what's the resonance? Okay, let's take it here. Take it into the amplitude solutions. So the amplitude, that's the A here. That's A here. It will equals to from this equation here. it equals to the M0 divided by M. The M0 is the driving force. And then divided by, it will be omega 0 square minus omega. Omega is our drive frequency. If we make this drive frequency equals to the omega 0, it occurs omega 0. Okay, and plus omega times omega 0. And this time the omega equals to the omega 0. Okay, and this one will be 0. It's only this left. So we get rid of them. So we get M0 divided by, that's the omega 0 square divided by Q. And what's the omega 0? Okay, I erased them. What's the omega 0? Omega 0 equals to the K divided by M. Okay, so the omega 0, we can write it down as the K divided by M Q. So it equals to the Q times F0 divided by K. Okay, that's the final results. So what does it mean? So if we have a probe here, if we have this probe, we apply a F0 on this probe. What will happen? The cantilever will bend, right? The cantilever will bend. The deflection of the band of the deflection of the cantilever should follow Hooke's law, equals to F0 divided by K, right? That's quite easy. So if we apply a F0, but this time we make F0 as this kind of oscillation drive. We make the F0 cosine omega 0, and we make the omega to be quite slow. Okay, to be quite slow, we would consider the cantilever will bend. The deflection should be something like F0 divided by K and cosine omega t, right? Something like that. Because we bend the probe, we bend in this way. The probe will oscillate, but again, its amplitude is it equals to F0 divided by K. But if the F0 cosine omega t, the omega equals to the omega 0, that means the omega, we drive the probe, we drive the cantilever to bend and make the frequency at its resonance frequency. What we get? We get the amplitude equals to the Q times F0 divided by K. So it means we amplify the oscillation. This phenomenon, we call it resonance. We call it resonance. Okay, that's just this slide tells us. Okay, that's just the story in our high school books. It tells a short story that Napoleon took his troops to go through a bridge, and his guys they're so good that they tap on the bridge at the same frequency, and then the bridge is done. That's the short story about the resonance. It's just here. If the drive frequency is same to the resonance frequency of your either bridge or this cantilever, and then this cantilever or bridge will have the resonance. The resonance means its amplitude will be amplified by Q times. Okay, that's the whole idea over here. Okay, let me take a look at time. Okay, we finished the mathematics here, then we take a short break. Okay, so for reps, for crabs, we don't talk. Where is the electric field force? Where is my EFM? We are still talking about the probes, say for half an hour. Okay, finally. Okay, so I write it down. The amplitude equals to QF0 divided by K. Under the phase, we can calculate by yourself. The phase will equals to the of course infinity, right? The phase will be tangent phase will be infinity, because the drive frequency equals to the resonance frequency. So the tangent phase will be infinity. So the phase will be half pi. The phase will be half pi. Okay, so we're talking about the resonance. So finally, if we have the interaction force between tip and the samples, and we say this, for example, this interaction force is the electric field force. What will happen? So how to do how to do the mathematics here? How to do our mathematics here? So we still write it down. So this one is something like that. D0 dt plus the drive signals cosine omega t. So I ignore, I directly drive at the resonance here. So omega 0t, and then plus the FPS. Okay, so how we process the FPS here? We know it's electric field force. We know it's electric field force. The electric field force is equals to what? To K, I'm sorry, I don't use K here. I use the column rule, 4 pi epsilon 0, right? And charge 1, charge 2, charge tip, charge sample, and the distance between tip and sample, right? That's the columns rule. So we have the electric field force here. How we process it? If we put this function, if we put this equation inside here, we will find this equation does not have a formula solution. So we want to make our case a little bit easier here. So we play some mathematical tricks. We use the Taylor equation. So the force between tip and the sample is definitely a function of z, right? If the tip is away from surface, the electric field force will be weaker. If it gets closer, it will be stronger. So it's definitely a function of z. So we can write it down using the Taylor expansion. Z equals to 0 plus its gradient Z minus 0 plus Z minus 0 square, right? Goes up. Okay, that's the Taylor equation. Okay, so for simplicity, we ignore the high order stuff. We only keep the 0 order and the first order. Okay, let's take a look at the zero order. The zero order means z equals to 0. What's the definition of the 0 equals 0? The probe does not bend, right? The probe does not bend means the force is 0. So the first order term is 0. So we only have the second order term. So the second order term, we can write it down as the dfts over dz times z. Okay, we find this term is similar to this term. So we can combine them together. Let me let me combine them together. I will put the combine here. I put the combine here. So the finally, the equation will be m dz dt equals to the negative k, and this one should be k minus dfts over dz times z, and the hydrodynamic force and the driving force. So this equation is almost the same as the original one. So we can definitely bring our result in, right? So we have the A, we have the tangent phase, we can get it back in. So, but what changes between this equation and this equation? This equation, if we ignore the FTS, we have this one. So at this time, the omega 0 equals to root square of k over m. But at this equation, the k changes. So we will define an effective k. It equals to the original k divided by the gradient of the force. What's our force? Electric field force, right? So we define an effective k, and at this effective k, we will say the omega 0 is changed to effective k. So our mathematical calculations just gave a brief result that if we drive our probes at the resonance frequencies, the probe will, the amplitude and the phase will follow the black lines, right? Will follow the black lines. Once we apply an electric field, this electric field will change the effective spring constant of the probe. It will make it stronger or weaker. It will make it harder or softer. And then as such, as a result, it will change the resonance frequency of our cantilever. So it means it will cause a shift of the resonance frequency. We drive the probe to oscillate at the original resonance frequency, but we apply a force. The resonance frequency shift. So we will definitely sense a phase shift or amplitude shift. So we detect the amplitude or phase. We can know this shift of the resonance frequency. We know the resonance frequency shift. We know the spring constant shift. We know the spring constant shift. We get this one. Okay, sorry, it's a long story, but That's how it happens. Okay, so again, so we have a probe, and we drive the probe to oscillate at resonance frequency here. So the probe will have a resonance. The amplitude will increase. The phase will equals to half pi. Okay, and then the probe sense an electric field, and this electric field will cause a force gradient, and this force gradient will change the effective spring constant of the tip. As a result, it will change the resonance frequency of the tip. But we drive the probe to oscillate at its original resonance frequency. If the resonance frequency shift a little bit, it will definitely change the amplitude and phase. We detect the phase and amplitude, then we can know how the frequency shift. And then from this equation, we get the gradient of this electric field force. Okay, that's the whole idea of our detection method. Okay, take a break, and then we go back to this. Okay, let's go ahead. So here is I summarize a little bit here. So we have a probe. We drive the probe to resonance to make it resonance. So the resonance means the drive frequency equals to its resonance frequency, and then we will get its amplitude is like this. The phase is half pi. Of course, the omega 0 equals to the root square of k over m. And then we came electric field force. This electric field force will is this kind of follows the Coulomb's rules, and we simplified using Taylor equation and make it looks like 0 plus its gradient times z, and then after that we put it back into the dynamic equation using the Newton's second law. We got this. We got the equation, and we found that it will have the same amplitude, it has the same phase, but the k will change, and the resonance frequency will change. And then how it changes? We know the positive charge. If we have the same charge, I'm sorry, it's the same direction charges. If we have positive or negative, it will have a repulsion. If it's repulsion, it will always be positive. So if it's positive, the force and the distance, it will be this way. So it means the dFTS over dz, its gradient will be negative, right? And if it's attraction, its dFTS over dz will be positive, right? That's the property of the electric field. So we can have, if we have a repulsion force, this repulsion force will make the probes looks stiffer. It will increase its effective K and increase its omega 0. So if we have repulsion, the K will increase, the omega 0 will increase. It looks like we make the probe to be more stiffer. If we have attraction, the K will reduce, the omega 0 will reduce. Right? That's in the qualitative way we will describe this. But if we are doing it in a quantitative way, how it will happen? So in the quantitative way, we're starting from the omega 0. We're starting from the omega 0. And then we want to know what's the how the omega 0 will change. So we will need to tell the resonance frequency shift is equals to omega 0 minus omega 0. Okay? So this one will be just the K minus dfts over dj and divided by K over M. How will do that? We play the trick again. So I said the basic of the AFM mathematics is just the Taylor equation. So we play this Taylor expression again. So I put the mathematics here. So the omega 0 equals to the K dfts dj over M. So this omega 0 is a function of dfts over dz, right? So I can write it down using the Taylor equation as omega 0 squared, omega 0 prime dfts over dz equals to 0 plus d omega 0 divided by dfts over dz, right? Times dfts dz minus 0. Okay? So what's this one? This term equals to omega 0. Right? Quite simple, right? So this one we already know this one is root square K over M. So the trick here is we need to find this one. Okay, we need to find this one. It's just I think this is the first year of your university mathematics. Okay, so we get it down. So this one equals to, so it's under the root square. So it's just there will be half. Okay, and sorry, K minus dfts minus dj divided by M, and at the beginning it's half, right? It minus 1, it will be negative 1, right? Okay, and it will be this one, and then it will times a negative 1. That's it. Okay, so it will be okay, quite simple. So times dfts over dz. So the next step is we consider the fts is quite small. So the dfts minus dz equals to 0. So it's also considered quite small. So this one can be quite simply to write down as negative 1 M over K and the dfts minus dz. So the results is just equals to negative 1 omega 0 dfts minus dz. So we put it back in here. We can get it. So this one I use the black pen to write it down as negative 1/2 divided should be oh, so I'm sorry, I forgot an M here. Sorry, there's an M here. Yeah, there is an M here. There's an M here. So the finally will be M omega 0. This will be omega 0 over this one will be K open 0 and dfts over dv. That's the final results. So this one, the resonance frequency shift will be proportional to the gradient of the FTS. So the final detection is, if we measure the resonance frequency change, we can tell from the resonance frequency shift, we can get the force gradient. So that's how we detect the electric field force in the AFM setup. So basically, we are just detect the resonance frequency shift. So in all your, when you read the reference about this AFM, if they want to do a quantitative analysis to get the force gradient, you will find in that in those papers, they are measuring the delta omega. That's the frequency shift. Okay, and we also have the phase things. So in the phase setup, we can also tell there will be a phase change, and this phase change we can just follow the same way to do this Taylor equation. We can get it back. We can get this phase shift is also proportional to the force gradient. Okay. Then let's do some AFM stuff. Okay, I put this equation here. That's our detection. We detection the resonance frequency shift. Okay, so then in EFM, what we will do, we will follow the tapping mode. First step, we drive the probe. The drive frequency equals to the resonance frequency. What's this step? Auto tune, right? When you do the tapping mode, you will tune the probe. What the tune the probe, you just set the resonance frequency. You set the drive frequency equals to the resonance frequency. Okay. Then second, we engage. We get the morphology, and then we open lift. Then we open the lift, and in the lift we set up this lift. We set lift height. This so-called lift height, we write it down as the Z lift. How it will change the electric force, right? It will change the electric field force. Once we set the lift height, the next step is we capture the phase and amplitude at lift step. That's the step. Then from the phase and amplitude, we know the phase is proportional to the force gradient. That's the stuff. And then this phase and amplitude imaging, that represents the electric field force. Okay, so that's our EFM way how it works. But fifth step. Some researchers they are just a classic researchers, in their study, they prefer frequency, not phase. So they like this one. So change to frequency shift. Change to frequency shift. So how we get the frequency shift? We do a brief instrument study here. So let me, I will put it here. Okay. Sorry, I will put it here. Okay. Let's just, for example, for sinusoidal, I'm just using the cosine function. For example, we have a cosine function. We have the z equals to a cosine omega t. I'm sorry, I used the omega 0 prime t plus 5. Okay, that's our detection. If omega 0 prime equals to the omega 0, we will say the phase shift, right? We will say the phase shift. So we write this equation using this way: a cosine omega 0 plus delta omega t plus 5. Right? That's how we do it. And then a cosine omega 0 t plus delta omega t plus 5. So if we study the frequency at omega 0, we will sense the phase shift. The phase shift due to the resonance frequency shift. Right? That's the idea here. That's the idea here. If we detect our signal at a fixed frequency, we will say a phase will shift. This phase shift due to the resonance frequency shift. Okay? That's the classic way. That's how we get the phase shift here. Okay? We have another way to think about this. If we know this kind of equation, if we know this kind of relationship, the phase shift is due to the delta omega. If we fix the phase, we make the phase as a constant. If we make the phase constant, how we can achieve that? Is we need to shift our frequency to make the frequencies is always at its new resonance frequency. So if we fix the phase, then we place the terms in this way. So we keep the phase at a constant. How in the instrument we do that? We have to change the frequencies. So in our instrument, we will get some loop. The loop is we detect the phase. We make sure the phase is at a constant. And how we achieve that? We will have a frequency shift. We change the frequency to omega 0 prime, and then we go back to detect the phase. If the phase is fixed at a constant, then we know we change our frequencies correctly. So this kind of detection loop, we call it phase lock loop. You may see it in some hi-fi stuff if you play around with those stuff. That's the famous PLL. That's the famous PLL. So in the classic way, we want to detect the delta omega 0 here. We will open the phase locked loop. The phase open loop will fix the phase term and then change the resonance. Then we change the frequency. And the software, the instrument will capture how this frequency changed, and then output this delta omega. You will get the delta omega here. And the delta omega or delta phase, they are all proportional to the force gradient. Either way will work. So you can use the phase locked loop on to get the frequency, or you turn off the phase locked loop, you get the phase. Up to you. Either way works well. But I still have to say, in the classic study, the researchers prefer the frequency. Why? Because phase has a stuff that the phase is period, means the phi equals to phi plus 2 pi, right? The phase is just it's a period function. You plus a 2 pi or you plus 330 degrees, the same thing. So sometimes this kind of period function, it will make the mathematical calculation kind of difficult. But the frequency is easy. So some researchers, especially those classical AFM researchers, they prefer frequency. So if you found your reference, if you are using the reference and you want to follow the same method in that reference, if they are studying resonance frequency shift, you turn on the PLM, phase locked loop. Okay, it's a function. It's an option in our software. You can choose to turn it on, or we can show you in our hands-on session this afternoon. Okay, so that's the whole idea of the EFM, how it works. Okay, so relatively easy. It's the same as the tapping mode. We just need to tune, get morphology, open leaf, and then capture the phase. If you don't like phase, turn on the PLL, look at the frequency. Okay, so that's the whole idea of our EFM. So the next, we need to do a more practical study. What does it mean? So here is some science reviews, and if you want to study more about the basic electric field stuff, you can study at this reference. But I would like to explain in my understanding about this stuff. So the EFM, we're always starting from conductor. Okay, the conductor. So if we are considering an ideal conductor, many things, aluminum, gold, carbon, anything. Okay, so for example, we have gold. Okay, so the EFM we do it like this. If we apply a positive voltage on the tip, it means the probe itself is positive charge, and we let it park on top of gold. What will happen? As we explained at the beginning, this probe is playing as the source of electric field. This electric field will polarize the gold, and after polarization, the top of the gold will be negative charge, right? And the bottom of the gold the bottom of the gold will be positive, and the inside the gold, the electric field is 0. That's the electric shielding, okay? Quite easy. But the probe is on top of the gold. It will sense the negative charge from the surface. What will happen? It will sense the attraction. I'm sorry. In my way, attraction is red. It will sense attraction. Right? It will sense the attraction. And this attraction will cause what? It will cause the phase reduced, omega 0 reduced. Okay? Right? Right? That's the idea here. That's the idea here. So, what we really detect here? So, for example, if we place this thing in vacuum, this interaction force will be what? This force will be 4 pi E pum 0. That's the dielectric coefficients of vacuum, right? And this one will be Q tip. What's the Q sample? Should be the same, right? The Q sample should be the same, equals to the Q tip, and the distance is the Z tip. So what's the force gradient here? The dF over dZ equals to the, I'm sorry, there's a square. Thank you. There's a square. So it will be negative 2 pi E pum 0 Z tip third Q tip Q sum. So if we know Q tip, if we know Z tip, this one we can calculate using the what the column equation, right? Quite simple. Okay. So if we place this thing in F, in this equation, which term will change? Which term will change? We still have the Q tip, we still have the Q sample, we still have the Z tip. Which term will change? Dielectric term will change. This one will change from vacuum's dielectric coefficient to L's dielectric coefficient. So we would tell from here, this so-called dF over dZ, we are detect the dielectric coefficient. We are actually detect the dielectric coefficient. So if we have the vacuum, it's something like that. And what's next? If we have a quite thin layer of the gold oxide, this term will be the gold oxide, right? So we actually detected this thing. So this EFM on this EFM on conductor, we are actually studying the dielectric. We are actually studying the dielectric. Of course, there will always be air. There will always be air. But if we have some materials, we'll get that. Okay, so that's the conductor. Then next, if I apply, sorry. If I apply negative voltage on the tip, what will happen? The surface of the tip, the surface of our gold sample will be positive charge. And the in our EFM, what we will get? We will get attraction. We will get phase reduced. We will get omega 0 reduced. We will get the same thing. And what's the interaction force? It's the same. It's the same. So, so we can control the quantity. We can control the quantity of charge on the tip by changing the bias voltage on tip. In AFM, this parameter is called tip bias. We adjusting the tip bias, we are actually adjusting the Q-tip. We adjusting the Q-tip, we are just change the Q sample because they kind of the same. And then, no matter we apply a positive bias nor negative bias, we always get attraction. Because this force is due to polarization of the conductor. It has nothing to do with the surface properties because it's conductor. It's always negative force. It's always attraction. We'll always get phase and omega 0 reduced. And from this force gradient, we actually get the dielectric properties of our medium, either air or the oxidized layer on the surface. Right? That's the conductor. That's our conductor, right? So if you have the next step is if your material is semiconductor, what kind of junction stuff? You are actually get what? We're actually following the same. We're actually following the same way. For example, carbon nanotube. Carbon nanotube. The carbon nanotube, we have two kinds of carbon nanotubes. We know the one carbon nanotube is more like a conductor. We call it metal-like carbon nanotube, and we have another carbon nanotubes. It's more like a semiconductor. We call it semi carbon nanotubes. So how we distinguish these two kinds of carbon nanotubes? So we put it here. So I have a surface. I have one metal carbon nanotubes. I have another one is the semiconductor carbon nanotubes. And in the EFM, we follow the same way. We will apply a positive voltage. For example, positive. You know the positive and the negative actually they are the same. You apply a positive voltage, and the metal carbon nanotubes, it plays the same as conductor. It plays the same as the conductor. You will get the DFTS or DZ, and this DFTS or DZ you actually get on the metal carbon nanotubes. This DFTS or TZ you actually get the epsilon over L, right? It's almost the same over L. But if your tip is on the semiconductor carbon nanotubes, they are not that easy, right? Because itself, it has its own dielectric properties. So this DFTS over DJ will be the epsilon of L absolutely plus the sample itself. So the EFM for the conductor or semiconductor it's a way to detect the dielectric coefficient. And in the dielectric coefficient, there is another way to name it as the dc over dz. C is the capacitor. C is the capacitor. Because in the capacitor, it's almost the same as a way to describe the coefficient, the dielectric coefficient. Because in a parallel capacitor, the C equals to A epsilon over Z, right? So dC over dZ is just a negative Z square A epsilon. A is a constant, Z is a constant, epsilon. That's our goal. So in the EFM, it's actually a way to detect dielectric coefficient, or in some textbooks you will tell it's detecting dC over dZ. That's the idea of this paper. Okay, quite simple. Okay, next we make this idea we make this thing more difficult. Third, we are looking at insulator. On insulator, what will happen? Insulator, the tips place it on top of insulator. As we have explained at the beginning, it will be slightly polarized because it's the dielectric coefficient is so large, so it will only slightly polarized. So, for example, if we apply a positive voltage on the tip, it will be slightly negative charge. So the interaction force between tip and the sample is so small. So we would say on insulator, we using this way, we detect the losses. The phase will change, delta phase will change 0, delta omega will change 0. Something like that. That's the insulator. But the insulator has another property. Insulator is so it's not conductive. But if we put some charge on the insulator, it will not move the charge. So we would say the insulator will connect the charges. So that's why in the winter you will find your wool sweater is fully charged, the electrostatic charges. So the insulator has another property, charge. That changed the story. So the sample itself, it has large charge. So when we play some sport, when our sample is something like that, we will have another way. We will put a tip on top of this insulator. For example, outside my samples, only somewhere is charged, and I want to detect which part is charged. What I will do, I will place my tips on top of the sample, and I apply low bias on the tip. And then, if the sample is charged, for example, if positive charge, it will what? It will polarize my tip, and then make my tip negative charge. And again, it gives you the delta omega reduce, delta phi reduce, something like that. So if I detect the phase shift or resonance frequency shift, it reduced, it tells me I'm on top of positive charge. Of course, if my sample is negative charge, it's the same story, right? It's the same story because I always detect the attraction. I always detect the attraction force. So in the EFM, I would summarize in this way. First, if we are looking at conductor or semiconductor, we apply peak bias. And this peak bias, positive or negative, does not matter. And we will always detect the delta omega 0 and delta phi reduce because we are detecting attraction force. And this attraction force is proportional to dielectric coefficient of the sample, or DC or DJ, same thing, right? And you can apply positive or negative, doesn't matter, it's the same. And the only thing is the absolute value of your tip bias increased. The shift of the resonance frequency or phase will increase. It's only proportional to its absolute value. Okay, that's the conductor and the semiconductor. And the EFM tells us dielectric property. Second, if I am studying the insulator, my tip bias will be 0. And the delta omega 0 or phase shift will be negative. And this gives us the charge distribution. Right? That's the idea of the EFM. So you can choose which setup is useful for your samples. Right? That's the way. Of course, if you want to distinguish between the conductor and the insulator, easy. Let's go back to our beginning example. We have carbon inside the rubber. That's the tire. You apply a positive or negative bias on the tip, and then on the carbon, you will get a negative shift of the resonance frequency. On the rubber, nothing. Right? That's the whole story of the EFM. The third one, that's this reference wants to tell you. We will have something due to the polarization. This polarization is either due to I apply tip bias or the charge on the sample. It's the same. It will always cause the first term. That's the polarization. And the second term is if I have a sample is insulator plus the conductor, and then the insulator itself has charge, and I also apply a tip bias. It will have the first term, the polarization, and the second term. The second term is due to the tip bias and the charge. Right? And at this time, finally, you may get repulsion or attraction. Something like that. For example, in practical, we don't have this kind of sample very much, but let's use this as an example. For example, I have a quarters. That's my substrate. On the onside of my quarters, I have two graphene. And this graphene, I use my tip to inject some positive charge. And this graphene, I use my tip to inject some negative charge. And then how I distinguish these two, right? That's some practical examples. And then I will get a tip and then make the tip bias positive. And then this probe is positive charge. And then I use it to scan these samples. And I will get on the quarters, because it's no charge, the frequency shift on the quarters will be 0, right? And on this graphene, because it's positive and positive, it will be repulsion. So the delta omega 0 here is positive. And of course here it's negative and positive. So the delta omega 0 here is, sorry, I should use red. The delta omega 0 is negative. If this will be your final EFM results, you will get two triangles. One is positive, one is negative. The background is 0, something like that. But at this time, this dfts over dz is not that simple. It's not equals to the negative 2 pi epsilon q tip q sample over z lift square. Not that easy, because you need to add this term, because the sample is already charged. You will polarize the sample, and the sample itself has charge. You will add another term. That's the difference here. Okay. That's the only. I think that's the this kind of example. There are not too much, but yes, it will be something like that. And at this time, you need to consider that. Okay. So. If you want to do some theoretical study, you get an idea that we are actually get the frequency shift or the phase shift, and this frequency or phase shift is we actually get the force gradient, and from the force gradient we need to tell the origin of the frequency of this force gradient. If the sample is low charge, this force gradient will be proportional to dc or dz. If the sample is charged, this force gradient is proportional to the charge distribution on the sample. Okay? Right? That's the whole idea. That's the whole idea of the EFM, and that's how we use the EFM for our studies. Okay, I think that's the whole story of the EFM. All the next, they are just more things to explain how it works, and there are some details, and those details we will go through that in the hands-on session in the afternoon. Okay, how to adjust the parameters, and I will show you in the afternoon's hands-on session. Okay, so yeah, about the probe, about the probes, about the probe choice. So the probe, in principle, we only need the probe to be we can apply the tip bias on the probe, because we may apply tip bias for the conductors. So we need to make the tip to be, we can apply the bias. In principle, if the probe is not insulated, any probe is okay. So sometimes you can even use your silicon probes, for example, scan-assisted L or OL Tesla, those kind of probes. But we still recommend you to use the conductive probes. Because the probe is conductive, so we can consider the probe is as a metal. And then we get here, we get the dielectric coefficient here. There's nothing to do with our probe, because the probe is a metal. If our probe is insulator or our probe is the semiconductor, this term will contain the tip. So we recommend you to use the conductive probes for the EFM study. But if you are using non-conductive probes, you can still sometimes get the results. Okay? And my substrate and my slides has something wrong. We don't need the sample to be conductive. We don't need the sample to be conductive at all, because we are applying electric field. We are just getting the electric force. There's no current at all. So the sample does not need to be to be conductive. So this slide is not necessary. We don't need to make the sample conductive. But this slide is just for one case. For example, you want to apply an electric field. You want to apply an external electric field on the sample. You want to change the charge distribution on the sample using the external the voltage. You need to add this step. Okay. For example, you want to study the samples under different electric field. You need this step. If not, no, the sample does not need to be conducted at all. Okay. So that's our study. And for the probe selection, we prefer it to be conductive. And the second, we prefer soft tip. We don't need the probe to be too hard, so we prefer soft tip, the soft candidates. So if you in the probe selection, you take a look at the spring constant on the back side of your box. Choose the one that has smaller pin. Okay. Okay, that's all. That's all. There are just more stuffs, and we will take a look on in the hands-on session. And the examples I have explained. Okay. I think that's all today. So thank you so much. Thank you. So we will go back at 2 p.m.
Yeah.
And we have another topic, surface potential, the KPF in the afternoon. And that's another story. So it may take maybe at least 2 hours. So we get the KPF done, and we go to the facility for the hands-on session. So today we may not have enough time to the hands-on sessions for both EFM and the KPFM, but we have some time. We have more time tomorrow. So today we KPFM and then hands-on session. Okay. Thank you so much.
Thank you, Dr. Liu, sharing. Thank you very much. Yeah. Since everyone a bit tired now, so I think it's good time to let them have